in a few different directions. So first of all, it turned out that we proposed similar topics for the longest, and because we collaborate on a regular basis on a thermal subsystem, then we decided, well, we may, collaborate on this. So this is an experiment along this axis in the first place. Second, it turned out that our slots in the schedule are almost back to back with a break in between them. So maybe we'll do just one, big big topic over the two slots, and maybe we'll do introduce what we think first, and then we'll do some discussion after, something like that. We'll see what happens. So this is the experiment along this axis, and it kind of is an experiment in the well, because this is a summary of some long series of discussions regarding interfaces that could possibly be used for driving different decisions regarding scheduling, driving hardware's features of various types related to latency and in general, or performance, if you will. So, okay. Thank you. First off, the general goal would be to allow the kernel to adjust the execution conditions for tasks depending on information coming from those tasks, because they know what they want, or they know what they are, what their properties are to some extent. Some information that cannot be figured out from things like task utilization or behavior or something like that. Usually there's a goal for every program that runs on a computer, and the author of the program knows the goal, or the runtime that runs it knows why it's running, hopefully, right? So that can be that type of information can be used. Right. I should maybe go a step back a second. We think that we need to focus on performance in the first place, and the reason why is because if we can, so basically, if we want to improve the execution conditions for some tasks, then we need to sacrifice the execution conditions for other tasks. This is like a zero-sum game. Something needs to lose for somebody to gain something. And if this is a zero-sum game, we can use the same information basically for energy saving. If all the tasks are willing to sacrifice their, performance to help others, basically. So let's say, okay, we'll try to improve performance for some tasks, possibly at the expense of others, and then use the same kind of information for improving the energy situation. We are not going to talk about deadline, by the way, because there is enough information there for already. So this is this will be about SCADA. Okay, so there's a problem in my view, and the problem is that the only metric that decides or is used to decide about the level of service is the task utilization or task size. And it may or may not reflect the needs, right? Because there are cases in which obviously this doesn't reflect needs. So for example, there may be a very small task that runs quite rarely, and it is very sensitive to latency. And when it is running, it has to run very fast because it has a short deadline. And a deadline may or may not be known, because if it is known, then it may be better to use the set deadline for it. But there are tasks like that. On the other hand, there are long-running tasks that will take all the capacity you can offer, but then they don't need the capacity really because they only want to make progress over time, and they don't care basically about the rate of the progress. Again, in this case, in both of those cases, the utilization doesn't the real needs. There needs to be a way to somehow provide that information to the kernel in general. Another problem is that utilization alone is very hard to use for driving hardware features that control performance, control bandwidth, that control latency, and so on, because you don't really know from the utilization, you don't really know how sensitive the tasks are and what settings to use for them. Okay, so yeah, that there is some zoo or some collection of control interfaces today in the kernel that can be used for adjusting the execution conditions in various ways, but only a few of them are at the task level. And opinions differ on how useful they are for the purpose, right? There are control interfaces at the CPU level or the rank level from the scheduler perspective, or global, and and people use all of them or try to use all of them in order to help individual tasks in various cases. I will give examples related to that, and that happens, in the field. And if you look at those interfaces, they don't really, they are not about helping individual tasks, because each of them has been introduced with a certain use case in mind, and they are used for different purposes than originally designed for in many cases. All right, so let's say about what's going on. So there is a web browsing use case in which things happen, like say a user clicks on a link. This triggers a lot of processing in the browser. You don't know in advance that this is going to happen, and it may not be reflected by the utilization of any task related to this, because before the user might be, I don't know, reading something for an hour, let's just say, and then he just clicks on a link, and then it triggers a lot of processing, and then the expectation of a user is that whatever happens will be reasonably quick, and it may or may not happen today because the kernel doesn't have any information regarding the expectation there. Another piece of this is garbage collection threads in a browser, which are basically very small from the size perspective, but it sometimes is necessary to run them quickly, because if they don't run in a specific time, they will not do any work actually. or any useful work. So they need to just start and do some work and very quickly. Size is small, so they on a hybrid system they will tend to stick on small CPUs with a little bandwidth. And benchmarks, which are designed to reflect the simulate the conditions that happen when users use the browser, and I will just expose all of those issues. On Android, I saw the Lukasz show me the tricks that people do to speed up application start on Android. There are literally profiles for certain applications which will bump up frequency scaling, frequency on CPUs by using CPU Freq SFS interface, just because this particular application is starting, and they just bump up the frequency for all of the CPUs in the system then, just in order to provide enough bandwidth for a single task. Camera capture, again, this is like, you want to make a photo, and there is something that's going on, and you want it to happen quickly. This is not guaranteed. It can take any time, basically, because the camera application is not usually used. It has to start, it has to ramp up everything, and there are multiple components involved. Hardware, not just the scheduler, not just the kernel. It all should be ready for the use case, right? And there are other examples. That it would be like too much time probably spent on going into all of them. So gaming is very similar to web browsing. So they like in a game, there are cases where a lot of things start to happen at once, right? Because the gamer did something and it triggers a lot of processing. And again, the expectation is that the processing will be done relatively quickly, or the user experience is not fantastic, right? This again is not guaranteed, because the metrics that are currently used may not reflect the case. And one of my pet peeves, so there are very background processes that run, that do things like index files on the user's hard drive, and they will get any bandwidth that they are given. They will just use it and run at max capacity available to them. But honestly, the work they do is not particularly useful. It is kind of maybe useful from time to time, but not necessarily super useful. So they could just say that they don't need all the bandwidth, and maybe they can do with a fraction of it, just as long as they can make progress. And this applies to any background type of task, right? All right. So the idea is, okay, so why don't we let tasks provide information about what to do with them? And this is a very, how to say, subjective list of desired properties of the API that we would like to have. And of course, you may or may not agree with it, but we tend to agree on it, right? Between the two of us. So yeah, I will not read all those bullet points, but yep.
Regarding the use case slide, the previous slides, those are client consume. There are not enterprise workloads. Like I don't see databases, I don't see web server, I don't see streaming server. I mean, you get the point, right?
Yeah.
True, but it doesn't mean that there are no such examples on servers.
Yeah. So if we can go back here, for instance, there is one useful information that there can be garbage collectors on servers as well, and they're actually, you cannot specify that your task is latency sensitive and you would like to collect as much as possible. And if you actually on the server control the throughput to the memory, you could pre-allocate for this particular task to consume the majority of that. So nothing prevents this API from doing this as well. But
yeah, so you know, if you asked about server workloads that have this property, so my example is like I was before I started to work on the kernel a long time ago. I was doing like helping people to set up web services with the database backends and things like that. And in those cases, the problem is that they again, this is hooked up to some web page, and when the user of the web page carries out a certain action, it will trigger a lot of processing on the back end of it, because it will run some say PHP script that will access the database. The database will have to do a search of some size, right? And all in response to a single event. And then the case is that a single event triggers a bunch of processing, and the user expectation is that this is going to be done in a reasonable time. And there are many use cases like that. It is not just those that we are talking about. These are just examples, right? You need to look at those as examples. So, okay, so going back to the list in the slide, so I will focus on a couple of points here. So the first point, in my opinion, and which is the most important one, probably, is that it should be suitable for driving different things, not just the scheduler. It should be suitable for driving hardware, bandwidth control, things like that. Should be suitable for other components, like, I don't know, a GPU driver, or similar for accelerators of different types that have performance levels. I can use, you know, higher or lower performance depending on the task properties, basically. If they know, they could be used for idle state control as well.
That will be a per task constraint or a system constraint?
I think that it needs to be per task in the first place, because the per task is needed for at least that subset of the use cases. But it needs, so I put as suitable for aggregation point in the list, which means that if you have a per task interface that can be aggregated at the rank level or the system level even, and the aggregate value can be used to drive other things.
To stack the constraints, right, of the different,
just
tasks.
to aggregate in some way, like, yeah. I don't know, make a sum, or maybe average, or maybe some other aggregate type of function. I don't know.
So from a user space point of view, I think there are C-scores where we define the property of a process where the structure is extensible, when we can extend the structure semantic. I don't remember one.
So yeah, so there are those things, and you know, it's not like I'm proposing or we are proposing a specific approach at this point. It is just like a kind of a wishful thinking at this point, right? This is what we would like to see, and then how it is done, it is kind of a matter of discussion going forward, right? But I think that it is important to define properties that or agree on a set of properties of this interface upfront, because then it makes it easier to kind of figure out how this should look like. We have some ideas. There are more slides in this, but they are ideas.
This is a new interface for all the quality of service parameters the task will have.
Well, yeah, yes, ideally, yes.
Okay.
Yeah.
Does it mean that, so there will be a bunch of parameters, right? That some of them we have right now already, some of them we talk about, like latency requirements, per task, slice length.
Yes, yeah.
These kind of stuff.
So I think that at this point, I would like to identify, you know, a set of parameters that could be used, and then came up with an interface that will be stable over time. We won't have to, you know, change a lot.
And is the requirement that, like,
Thomas? I'm occupied. The other.
Yeah, I agree. I mean, the problem is, up to now we have added tons of POC interfaces all over the place in subsystems, and then we expect that all of these subsystems work nicely together, and but there's no central place where we have that information and where this data can be coordinated in a sensible way. And also, because you want to do a response reaction, so we want to have a feedback to the process, what it actually gets or is supposed to get from a particular system.
Yeah. So that is the part I didn't think about, but yes, I agree that we need to get it needs to work both ways. I mean, some information going from the process to the kernel and the other way around. So the application knows, you know, what the conditions are, right, at the moment, and then it can adjust to them possibly. All right, but
yeah. So Dietmar, I'll just ignore what we have right now, the various syscalls, ioctls, and sysfs knobs, and what it is. Just ignore it, please, for the discussion's sake. Right. When we go and really say, okay, we have one focused area where we collect this information and where we distribute it and also aggregate it in a sensible way, then I'm pretty sure that a lot of the problems we have today can be solved that way.
Right. So that's the idea, basically. Okay, so now a couple of kind of loose observations about various interfaces that can be kind of useful, maybe. For as part of this solution, not necessarily as that solution, but okay. So first of all, I would like to clarify the terminology a bit. What performance really means, and how to maybe control it, right? Yeah, control is the good, or adjust it, right? So there's latency, and there normal or usual definition of latency is the time between, you know, the trigger event and the response to it. But then this there are multiple components of it. And then one of the components is say the frequency a CPU is running at. And this is a throughput component. because obviously it is related to how quickly things happen during this time when the response is being prepared, right? So in my view, it would be good to have an idea of raw latency that can be somehow separate from this throughput component. So we talk about the latency unrelated to the current speed that we use. I don't know if this is possible, but anyway, there's throughput, and again, it's average. It's raw and which contains some latency component, because say for example for tasks on a run queue, the throughput depends on how many of them there are, and also depends on how quickly they wake up and then process things and so on. So there is some latency component of this throughput that can be measured this way. If we can somehow talk about raw throughput, then without this latency component, then latency and throughput are become orthogonal to each other and then can be treated as different axes. So I don't know to what extent it is possible to separate throughput and latency, to be honest. So we probably need to accept the fact that they will be somehow interconnected to some extent in some cases. But those are two parameters that I would like to be able to use for adjusting the execution conditions. But there are others possible. Like we talked during the lunch today, we talked about, say, the case when there is a C group with a bunch of tasks, and it may be there may be different policies for the C group to wake up. Like somebody may want their C group the tasks in their C group to be woken up on different CPUs. Somebody else may want the tasks in their C group to be woken up on one CPU or packed in other words. And it doesn't necessarily fall into the throughput or latency category because it's just about the way, the preferred way of handling this workload. So okay, so let's see. Let's start with throughput, and if you look at the NICE interface, it actually it's not a bad interface at all. If you consider this as a throughput reduction tolerance or sensitivity, right? So by setting a NICE value, the task the information coming from NICE can be interpreted as a tolerance for throughput reduction, or if this is positive, or sensitivity to throughput reduction if this is negative. It is a number, so it can be easily aggregated in many ways. It doesn't have to be from -20 to 19, right? The scale is like a matter of an agreement, but it is kind of provides the useful information, a useful piece of information regarding the task that can be used later for various things. And if you think about latency, the case is really analogous to this. So latency NICE, in my view, it's not a bad idea entirely for this reason. Yeah, and it.
So when we talk about throughput and latency, are you thinking of this as sort of an absolute thing, or is it a relative thing? And how do you measure throughput?
Relative.
What's the metric?
Relative. So I don't measure it. This is about tolerance and not about.
But how would if you express some value of throughput, this task requires 40.
No. So it is. No. So this is relative rather than absolute in the first place, right?
So both of them will be relative.
So both of them would be relative. Now,
which means the bullet 3 on your previous slide about portability, that's gone, right? You can't just set a value and expect it to multiple platforms.
Well, that's probably because, yeah, we don't have the closed feedback loop. But if we can notify from the kernel to the user space, then we could adjust.
Yeah, then you have a relative, right?
Yes.
If you have a relative sort of metric
Yes.
or tuning knot, then that could work. You need a feedback loop.
Yeah.
Good.
So as I said, these are pieces of the thing, are not like a complete solution by in any way, because they can't be, right?
I just wanted to understand where you're going, because the throughput thing, I think, is really hard to define.
It is
what it should mean, other than it can be an abstract knob saying, I
Well,
want a
so
higher throughput, I want a lower throughput, and that's essentially it.
True.
Right. So, that's why I'm saying relative. So the task that provides that says I can tolerate throughput reduction can be used as a so if there are two tasks, right, running.
Mm-hmm.
One of them has a high throughput reduction tolerance, and the other has is throughput reduction sensitive, right? The idea is that the task that is sensitive run faster, meaning at a higher frequency, possibly at the cost of the other task. So, for example, if there are two CPUs to choose from, the sensitive task will go to the more capable CPU, and the other task will go to the slower CPU, or something like that.
I'd like to quote again the presentation given by Thomas in November in Kernel Recipes, that it gave for me the most convincing definition for throughput, which is throughput is good if I rarely preempt a task that holds a lock.
So
you see what I mean?
Not
at all.
When I'm talking about throughput, so let me go here. What I mean is the rate at which the work is done.
Okay, so it's operation per second. All right.
Right.
No. Could you elaborate again about the difference between throughput, the raw throughput? I'm afraid.
So yeah. So this is something. Let me try again. Okay, I may not succeed, but anyway. So I think that the rate. So the something that I call average throughput is contains a latency component, because, or includes the latency component, because it depends on in general, it may or may not, but in general, it contains a latency component because it depends, say, on how much latency there is generally in the system, because this slows down the processing. So if there is a run queue full of tasks, say, the throughput of each task depends also on how much time it takes to wake up every task in a queue that will run before it, or in addition to it, right? Because those wake ups will happen in cycles, and that may depend on various things. Like there may be there may be some bottlenecks somewhere in memory, things like that. And so this is latency included in the throughput number. And ideally, I would like to think about throughput that is just measured when the task is running and not is runnable, for example. So the throughput of a running task. So it does it doesn't include this latency thing. That's the I can explain it. I don't know if I answered your question. So right.
So I have a question about NICE now in the context of EEVDF, because it adjusts deadline. So is it still in your mind mostly a throughput mechanism? Because it will, if the tasks are ordered by deadline and you use NICE, it will affect latency as well.
It will, yeah. The NICE is will affect latency. So that's why I put a bullet point in the slide regarding row throughput, which is yeah.
There's one another question at the end of the audience.
Other than the current NICE. So I'm not saying that the current NICE is the most suitable interface, but it has nice properties and it can be used as a model of an interface for those performance components.
So Rafael, when you say raw throughput, you probably are only referring to the frequency and probably the capacity on which it runs, because we don't want to worry about.
Yeah. So roughly, but so let me repeat what I said when I was answering jury. I said a throughput of a running task, right? A throughput of a running task, which means the task is running on a CPU. It's not runnable, but running on a CPU, and it gets some level of throughput then. And then it doesn't depend on the latency, because it's just this task running. And so it will be the frequency, but also some bandwidth. It may be some bandwidth allocation on the interconnect and things like that, right?
Yes, I will show you one example where we can increase actually throughput. That would be one of the slides.
All right, so we are spending a lot of time on this. One thing I wanted to say in addition to the above. So if we have that information that say some tasks say that they don't really care much about either latency or throughput, that can be used as an opportunity to save energy, because for a task that is more tolerant to performance reduction, the kernel could reduce say if the CPU frequency or similar, and that the effect of that could be the same or similar or the same as running beside a less tolerant task, right? So instead of, if we only have tasks that can tolerate reduction of performance, then yeah, fine, we can reduce the performance just as though that there were other tasks running in addition to them. And this is the way we can save energy. So this interface can be used as a source of information for energy saving as well as for performance improvements on the tolerance side, in principle. Yeah, so this is kind of a set of loose ideas about how this could be implemented at a high level. But I don't think I want to spend a lot of time on this particular list, because as I said, these are loose ideas and actually subject to to discussion and so on. So I will let now Lukasz talk about how to address the use cases that we mentioned before, if this interface is available. So,
I have the mic.
oh, you have the mic. Okay,
Yeah, but I would need the control.
Okay, so we can continue after the break. Okay, so that it is a good place to maybe
Sounds like
a break and then continue later.
Thanks. One, two, three. 1, 2, 3. Okay, welcome back after the break. So I will continue what we have started with Rafael before the break. And this part will be more focused about the hardware design and how this hardware can impact your perceived performance or latency. And the slide that you can see now is describing the quite modern hardware design on a mobile phone, where you have L3 cache, and on top you have the different types of cores. So those CPUs, they have different microarchitecture. They share this L3 cache, and then also they are made differently from the cells point of view. So they might use a different cell size, but that allows them to either save the power or get the higher frequency. But they share this L3 cache. It wasn't like that a few years ago. We used to have L2 cache, which was per cluster. So those CPUs are in the cluster, and you could have L2 shared between the local CPUs inside the cluster. But the thing has changed, and now we have even L3 cache. And as you can see here on this L3 cache, we can have different slices that you can actually turn on and off to save the power, which opens yet another dimension for optimizations for the power saving, but might create some issues for your application, which when the application is not aware of this hardware, the hardware doesn't expose this, then you might get different performance. Also, all of these components that you can see here, they support DVFS, so they can scale dynamically voltage and frequency, including the interconnect or the network on chip. They all have their own performance levels.
I have to mention that I personally wouldn't like to expose anything from the hardware to the user, to applications. directly, because that's going to be that wouldn't scale basically. So the interface I was talking about is one of its purposes is to abstract the
Yes,
information that can be exposed, and
that's current situation of the hardware and the way how it exposes the control. That what you have mentioned, I showed you about this frequency knobs that they can tune at runtime per those devices.
Yeah.
But this is not the proposal. This is the current situation which is there, and we actually cannot control fully those interfaces because they can be implemented by the vendor. So we don't even know the scale if there is some knob. But they are all involved sometimes in the particular use cases.
right, and moreover, even if the given driver or given subsystem in a kernel would like to participate in some latency or bandwidth provisioning, let's just say, of control,
Yes.
then it has no information to do it.
Yes,
today.
That's current situation.
For the bandwidth provisioning, there is already an interface, a framework in the kernel where the driver can ask for their memory, so peak and average bandwidth between two endpoints.
Yeah, it can ask, but then it doesn't know when to ask for it, or what's running, so how much of the bandwidth it needs at the moment.
Yeah, we expect the driver, at least the driver that are using that right now, they know what they need. I mean, typically an SD card, a USB profile, they know in average what is the average bandwidth that they need.
So unless the application running tells something about itself, that there is not enough information to really do that. Yes, you can mechanically. So there is mechanics in various places for doing bandwidth control. Other things. There is mechanics, but there is no translation between the application that's running and may need or want something and that mechanics.
Yeah, one example is resource control, where you have memory bandwidth and eventually L3 partitioning and stuff like that. But that's not based on application input. That's based on what the sysadmin sets up.
True.
Right, and it's exposed to user space.
Yeah,
pretty much raw. So pretty much raw, exposed in a raw manner to the user space, right? So right now.
Yeah.
True.
Yeah, but the important part is that this is mostly used on setups where you really the operator or system administrator knows exactly what the profile of these workloads are, and he can partition the machine in the right way.
Yeah, and the profile doesn't change over time.
No,
right?
it's very static. But if you look at these kinds of things, and it's definitely true for cloud container workloads where you don't know what the hell is going to run on it. So if these applications can actually express some constraints or some wish list, I mean, they might get it wrong, but then the kernel can do something about it.
Yeah.
Yeah.
Okay, Lukasz, sorry about interrupting.
Yeah, no worries. Thank you for the feedback. Yeah, we also have in this L3 cache this feature which is called MPAN. That's the memory partitioning. We are not hooked into this REST control yet, but that's ongoing as far as I know. But yes, but yeah, as you mentioned, this is the user space control, but we are discussing slightly different thing now. But coming back to this L3 cache, so those power management features, they are also not controlled in the kind of per task way. So they are not aware of what is going on in the system. They try to guess. And I will show you some examples you recall this list of the examples and how we could actually improve if we know how to act on those devices which are involved in the processing of the workload. Then what can be done when we have a better knowledge of what is needed from the hardware point of view, let's say shorten latency or higher throughput, and how we could measure possibly and agree about this measurement way. Maybe after agreement we could run some validation tests and some tools for this if we go forward. Okay, so the first on the list was the web browsing. Then there was this application launch time or the camera capture thing, and then the gaming. And I have those examples where I will try to show you what.
Can you go back to the
Yes.
previous slide for a while? So the gaming part in particular is interesting because it could benefit from the feedback, from the backward feedback that Thomas was talking about.
Yeah.
Because it could, for example, adjust the frame rate to the conditions that are available, right? It could just reduce its bandwidth usage.
Yes, so there are already publicly available specifications for something on Android called ADPF, an Android Dynamic Performance Framework. It tries to address some of those issues mentioned in the gaming section. They need some implementation from the vendor to interact with the hardware, but they have this closed feedback loop. So not only reducing the frame rate, they also allow the game developer to change the quality of the game. So let's say reduce the shadow quality or reduce the number of objects which are rendered. So, and then there is this feedback basically every frame. But this is for relying on the knowledge of the vendor if the vendor will implement the backend for this mechanism for the game engine and for this daemon, which interacts with the game engine. So there are some areas which are interesting and they are evolving. And let me mention them later in this gaming. But let me start from something which is this web browsing problem. So as Rafael mentioned, you can have different scenarios while using the browser. This is one of the scenarios where you test the phone and you want to have a nice score because you compare two different phones from two different vendors or different generations of the phones. And there is a set of benchmarks that's the test suite. This particular example, that's the speedometer. It has a bunch of JavaScript frameworks running the same type of work, but stressing the CPU quite a lot. Not only one CPU, but actually the whole subsystem, because that browser, it has to do some magic with code, and that involves different components of this SE. 1, 2, 3. When you look at the performance numbers, they can be improved. I have some results playing with different settings, and some of those they have been discussed on the mailing list already. Vincent have improved the utilest some time ago when I mentioned one of the problems with this particular workload. But there are some others, and as you can see on this example at the bottom, which components are heavily involved in this processing, and they can change their performance, actually, each of them independently, basically. And this is not standardized what should be done at that processing workload type. But they have quite common paths, so they work on memory, and they would like to do this efficiently. And what metric I have used, this is like a simple metric, which is the instructions per cycle. And that actually, so if you measure something like this using even simple perf on Android or perf, then you can just derive that ratio easily. And what that ratio tells you, it tells you how much actually instructions you have done in cycle. And the important thing is that it can give you some rough estimation if the CPU had the problem or not, if you compare one run versus the other run, and if you start playing with those components down the road, down to the main memory, so to the DDRAM. And because the modern hardware evolves quickly, those frequencies which are involved, they have quite vast region of the optimization space. And yeah, what should be picked for this kind of workload? Well, the workload doesn't tell anything. So if you just pick the right numbers for those components here, then you can get quite high score. And this is on some recent phones.
So yeah, I think the point here is the relative difference between the scores with and without the tuning.
True.
Right.
So this IPC is not only related to the type of the CPU that you are running on. It's the combination of many different things. So if the processor, which is quite aggressive in the prefetching of the data, speculating about the branches, if you can shorten the latency, for instance, to the L3 cache or to the memory controller, you would observe that in this high-level metric, which is IPC. Some low-level metrics like a backend stall or cache misses, or the time that you spend in those moments when you have to wait for the data, for instance, when you're doing this garbage collection or some memory allocation. This is sometimes waste of time because you haven't increased the frequency for instance, L3 cache, which means you increase the latency response for the data traveling to the core. And yeah, that manifests itself in this high-level metric IPC. Yes, Vincent?
Some people are already scaling the interconnect based on the utilization of the CPU. It's per CPU, it's blind, I agree, but they are already doing that.
Yes, so that was my goal to actually mention this. So even if you observe the utilization of the CPU or the U-clamp of the CPU, of this particular state of the CPU, you might not derive the right answer if I should increase now or not. This is just a heuristic.
I agree that there are probably cases where they're wasting some DDR cycle because they are not really used at the end. But yeah, I agree on that. But just to say that some people are already doing that at more coarse grain.
Oh, of course, they do, and they do. So I talked to a person who was trying to make a business by providing an AI application that would tune all the settings of a system using some kind of machine learning to reflect the workload, say needs or behavior, and this way, everything like CPU idle, CPU free, other things, just taking some inputs and then to optimize all of those settings for this particular workload. And yes, the people do that. I'm not sure about how much money they made, but.
So I'm not saying. I mean, if we can even go deeper in the fine grain, that's fine. I just wanted to mention that this is already something that is happening in current products, scaling with the utilization. Except that's right now it's only at CPU level, and that's probably not enough in some cases because there are some ways of.
I should mention one thing that I forgot about. So that there is information available in the kernel. Like utilization is one of those pieces of information that the kernel can figure out by itself. But there are pieces that it cannot. And
yeah, I'm fine with that. I'm not saying that everything is already there. I'm just saying that there are already things that might need to be improved. Yes.
Yeah, I got your point. Thanks for the feedback. Yeah, so as you can hear now, there are already some experiments to involve some more information into this decision chain down the road to the main memory. If that's the right one, we have to discuss that, but there are actually experiments already ongoing. Yes?
I wanted to mention that on Intel platforms, the clock or the L3 cache scales with load. But that's a microcontroller-driven algorithm, the anchor frequency, right? So
yeah,
this interconnect you were mentioning is operating system-driven or hardware-driven? Okay, so this is a different thing.
Yeah, so we try to combine those two words, but they are slightly different sometimes. So as probably Vincent is referring to my world, ARM platforms, isn't it? You are referring to ARM platforms. It's
I was mentioning only some ARM platform. I don't know much on Intel.
Yeah, me too. This is another example. This is the application launch time, how to reduce the application startup time. It's actually a useful tool, the Perfetto. You can actually trigger the record of the application start time. That's the top bar here. It will tell you using Google metric how long it takes to actually launch the application. So quite easy, but quite useful as well. And that example was a Gmail app. So I usually waste like 560 milliseconds for launching that app. If you apply some heuristics for those buses and devices, you can actually reduce by roughly 100 milliseconds that period. And this is quite useful metric for us because that launcher, which is quite common on Android, you can install even different custom launcher. But if that application can express itself that there will be quite a lot of tasks involved, there will be memory involved, even the storage. So the I/O and also interconnect network on chip, because that will go through a network on chip as well. Then you need as well the bandwidth to the main memory. So you can actually, yes?
One thing to mention is that in this particular case, because on Android, every application is started by launcher.
Yes.
It would be just sufficient to make launcher a sensitive process, and then this information may be used to speed up the startup.
Yeah.
For every application.
Another question. Yes.
Yeah. In this particular case, does it really make sense to have a peak of energy for the gain of just 0.1 second, which is not noticeable by the user?
Well, it's actually one of the key KPIs for vendors.
Oh, okay.
So quite a lot of partners are interested in this metric. I don't know if you, John, from Google point of view, could confirm this.
I don't know if I can speak to specific metrics, but I think app launch times are important. They're things that impact users because you do notice. It's one of those things for how the phone behaves, the smoothness of it is something that.
Also, it wouldn't. I think it wouldn't increase the energy usage that much, because if it takes a short time to start an application, approximately, then the energy usage is not going to be huge, relatively, right? Because you will adjust the settings when the launcher is running, actually, and then drop again to the lower levels, and then
I agree. So even if you pick a bit higher power, Daniel, then you shorten the time when this power is used. So total energy should be as well not that pessimistic. So
the one thing I might note here, so at least for your example, the hint, I guess, that often is used at launch time is somewhat time bound. And so that app launch is only for a certain period of time where they want to have all that boosting going on. And then they want to go back to kind of the more power constraints.
So so all of that needs to be dynamic. So I think that it can work in a couple of ways, but one of the ways it can work is that the sensitive application can mark itself as sensitive only for a specific period and then drop the setting. It can be made work in some other way as well.
So I don't think you can have the applications tell yourself if you're sensitive or not. It's got to be middleware, because otherwise every application will tell you, I am the most important in the world.
I should say task.
No, even task. I think that these are like third-party applications. The developers will say, I am the most important in the world, push me all the time.
Okay, so
it's got to be middleware. That's what Android does.
One more comment, I guess. There is a difference between application and that interacts with a middleware and a task that runs on a CPU controlled by the kernel. So they are, because the application can say, okay, I'm background, which doesn't necessarily mean anything to the kernel, but it means something to the runtime or middleware running.
So in Android, the middleware decides who is background, not the app.
Yeah, and then the middleware can use this to set the hints for the application or for a task that it is running, like launcher, which is not an application, but it is a task, right? It can be given a certain hints to make it run faster.
I think I know from where we are coming, Quantum, from this security concern in Android, like the ADPF task per task, it votes for this syscall. The normal syscalls are not allowed to do for the uclamp thing, for instance. You have to respect something like untrusted applications from the system point of view, kind of, right? Isn't it?
Yeah, it's not even a security thing. It's just if you let applications decide if they are important or not, they will all think they are. And so that's why in Android the whole boosting thing is not application driven, and the knowing if an application is in background or foreground is not controlled by the applications, right? It's controlled by the core Android and middleware.
So there's the system control of those application tasks, but there is also the application feedback to things like ADPF. And so that is application. Yeah, for this one, this is not yet, but I would say that it's kind of both, because you do have the cases where applications are requesting quality of service for specific threads that they have that are doing specific tasks. But at a large thing, that all has to go through some sort of system how to decide whether or not that's okay.
Yeah, thanks, John. Thanks, Quantum. Let me continue. So one of the last is this gaming use case. There are, or maybe I will go back shortly here. So yeah, on Android, we actually have those mechanisms that we can probably reuse. That's the ADPF. They already interact with those tasks. The ADPF is just like a daemon with some backend provided by the vendors to understand what could be done on the hardware and provide this feedback to the application. So it's like a controlling algorithm plus some translation, understanding what is going on the hardware and how you can interact with that hardware. Yeah, we could maybe cooperate with that for experiments. Here is a gaming example. Some of those tasks that you can see in a game when they are running, mainly using two major game engines. They know what they do. Those game engine developers. For the developer who is working on the particular game, that it's actually majority of the work is done already, because they can just reuse some stuff. But from the OS point of view, those game engine developers, they cannot express precisely in time what they would like to have. That's the new thing that Android is pushing forward, this ADPF. So the thread from the game engine can express itself and ask for some, let's say, a better performance or better so throughput or latency. So based on feedback loop, it can express itself like last period wasn't good enough for me. Then how this is translated by this vendor-specific code, it's up to the vendor what it will do with the hardware. But as far as I know, there is no standardized definition of the latency versus throughput. But those are the example tasks which can benefit, actually. Two of them, as you can see in time, the x-axis, some of the tasks, they don't behave like normally. They could run and then suddenly they could cause some spikes and they manifest themselves on this utilization plots, and that's quite short spikes. The game engine would probably know what is going on, which means, for instance, some new scene is loaded. We need new textures. So probably page fault will happen, or maybe not even one. And then if you could change the current behavior of that, the compute system, to actually reduce this penalty of the page fault and make it served faster, that might help them. As well as the second one, that's the shader compiler thread. This is an example that when you usually run a benchmark, you don't see this because those benchmarks, they are coming with pre-compiled shaders. In the normal world, you compile shaders in the games. So you would like maybe to express this as a latency sensitive thing, and boost some part of the systems if we do the right translation. It's currently not there, as far as I know, in this design. But those are examples where you can actually make a difference. And then you could see them on metrics like the maximum frame rendering time, which we could agree on this, and average frame rendering time, or even some other plots like this statistical plots, like the histogram or whatever. We can compare how good this could be if the task could express it themselves and making our hints to the system, and then the kernel could understand them better. Yeah, so that's the last slide. We can...
Yeah. So so this is the last slide. Again, this is something for discussion from our perspective. It's like our point of view or ideas regarding this. I personally think that we desperately need to add some way for tasks to be able to provide information regarding expectations or sensitivity to the kernel, simply to get better service, or on the other end, to say that they don't need fantastic service because they don't do super important things, and that could help to drive both performance and energy saving, and then it is important to be able to use this information to control various things, various system components, including the scheduler, but not only the scheduler. And again, this needs to be on a per task level, because some adjustments need to be done at that level, and then should be suitable for that for aggregation to be applied at the CPU level, at the system level, in various places.
I want to make this remark. So this task that I see, as I said before, they look personal computing kind of stuff and tasks, and I see a certain interest around mobile and ARM, and we say how this task communicate the importance, etc. But when we move the focus on the Intel architecture that you have described yesterday, we have a completely different approach. We have HWP, which we all know and love, and last at the Hot Chips conference, this power architect for the client group, Efraim Rotem, someone that I sort of follow in the space of Intel, presented the Meteor Lake architecture, which is hybrid, so big and little. Yeah. And in that context, HWP is not an algorithm. It's not a code that you write, but it's actually a neural network that is pre-trained by Intel on those tasks. So it was observed that it's easy to write an algorithm that can filter out all those spikes and all those false positives. But when Efraim, this engineer from IFA, I believe the Intel Development Center there, looked at the traces and correlated to his test and say, this spikes it's a click. And so he was clearly seeing all those, as we're going to make a neural net into our microcontroller and call it a day, essentially. So the question is ARM going towards that? I don't know, in 3 years, you're going to have an autonomous system with some neural network in the hardware, or there is a different roadmap and strategy where you say, we are the low power sort of chip and we kind of take it easy and want to have this in the West.
So, I don't work for ARM, but I think that you are asking this question in a wrong forum. So if I worked for ARM, I would probably avoid answering this question.
Yeah, I cannot answer it. This is yes or no, because that's
I want to say it's completely different. Like it's like night and day. Completely, I don't know. Well, it's
yeah, so Giovanni, even if I knew the answer, then I couldn't tell you. I'm sorry.
So I've been trying to look a little bit at some QoS stuff because it's been a big topic of discussion around my team. And there's kind of this aspect of what we have with ADPF is a similar sort of cyclical, we take what you expect and then you provide measurements to the system, and then it tries to kind of boost or lower you so that you match your expectation. The proposal yesterday about having the period end signal would be really valuable for that, because I think that would allow us to kind of communicate more directly to the kernel what we want there for that sort of period and adjust quickly. Because to some extent, it's like a secondary cycle over PELT, where PELT will get us there eventually, but like this kind of speeds us up a little bit and better tracks it without all the interference that Peter was talking about. That also, though, is kind of separate with these that periodic work style is separate from the aspect of needing aperiodic. And that's what Stephen was commenting last night, was event-driven like signals, where we say, okay, we're not doing anything for a while, and then suddenly there's a lot of work to do. And we need to be able to say, we got to go fast right now.
Yes.
And so trying to figure out in the API, like, you can say, yes, I'm latency sensitive and that, but then sometimes there's more specific time periods where it's more critical to boost rate then or not. And so as far as an API, I'd just be curious if folks have thoughts on that.
Well, so we haven't discussed that deeply, the API that needs the two variables for the two signals or one. But as far as I know,
so as far as I can say, it's about, or as far as I understand it, is that you're making a point that those there is a need to provide like more precise information regarding the time frame, right? Of what time, how much time it will take to what time frame is relevant for this event, right? Because this is basically, if you don't fit in this time frame, then you may as well not do anything, because it doesn't help anyway, right? So that could be a piece of it, I think. I don't know. So one of the goals of this session is to collect like feedback on what people would like to be there in this interface, and then maybe figure out how to design it. when we know the various useful things. It might not be feasible to cover all of them. Like, I'm sorry for skipping the unicorns in the list of wish list. This is like, yeah, my fault. But anyway, yeah. So if you agree with the idea that an interface between tasks and the kernel is needed for this, please talk to us, and then we say what you think is important to you in particular. And it doesn't apply to just client people that work on client systems. The server people are also welcome to say, to provide feedback, right, on what they need. And I know that there are people who care about latency on servers as well, like database people and similar. So yeah.
So I think that this having a pair task interface is something that everybody would like, but we haven't been able to figure out what should be the right interface. I mean, we made several trials without success so far. I would just want to say at the beginning, you say that the deadline scheduler is out of scope because they already have all the information. So why not reusing their interface?
We'll probably see from experience that the interface is kind of seems to be hard to use, because people always say, well, how do I specify the runtime? So I'm not sure if you want to adhere to that. Maybe if I would say we want to abstract, try to be as general as possible, and then figure out what to possibly reuse.
Right. So I think that one of the problems with deadline is that it is difficult for people to figure out what parameters to use there.
Yeah, it's just that we try to have some abstracted value, but it seems that doesn't fit. There, normally, with a deadline, a runtime, and a period, you're able to provide your bandwidth, your latency, and maybe, with a long deadline, your throughput as well. So you can provide. I don't know. It just
also there is one more thing. The deadline, in many cases, the expectations are really relative. I mean, they are not hard requirements.
No.
They may be like, okay, give me the best throughput you can, but
we are not. I'm not saying that we should put hard constraint on that, but just the interface is there and can provide already a lot of information regarding your task. Now, I mean, we are CFS or fair task, so we can't do more than what we are designed for.
I guess the point is that we could use the parameters that are used for deadline to describe task properly.
No, yeah, that's my point. Using this parameter not to become a deadline.
I was going to say, I think that works really well for periodic loads. And I think for aperiodic stuff, it's a lot harder for people to understand what they need to do, because they just want to be, as fast as they can for the next bit, right? And so it's
yeah. So let's something like this, John. That I want to just compile this shader, and I will
as soon as possible.
Yeah, as soon as possible, and probably.
I would tend to agree. Thinking so, the interface is based on SCADAT, and that is extensible. So maybe we could, in principle, extend that and maybe not use every parameter for every user. If you don't know the runtime or you're not sure, maybe there is something else you can specify still with the deadline, maybe. So it can be.
I would say, yeah, that's the point. If you don't know the period, I don't know, -1 mean I don't know my period. So that's mean I'm an event based and no more periodic one.
Yeah, but on the other hand, if you are a game designer and you know what is going on in this spike, and you know that I would need like the latency from the memory or the bandwidth, you should be able to express that at that particular moment, because that task could do any different job, and that particular moment could be. No.
So I don't, Lukasz, I actually don't don't disagree with Vincent. It is feasible to use those that interface, but I would extend it by adding like flags or similar for special cases.
Wouldn't another approach be more like suitable here? Like we talk a lot about like a new interface. Nobody knows how it looks like, and we bring up those system which should be connected to this interface. Wouldn't it be the better approach to come up with a proposal of this interface and try it out in one of those runtime environments and connect more than the scheduler? Like,
sure, that's the next. Yeah. We would like to have some idea of how to kind of, because we can repeat that exercise like forever, because we can propose different things and then right? Yeah, but we would like to have some input like on how to how it.
There is a question from John.
You know how to approach to this.
So I was going to say there are a number of existing things. One of the problems that we have in Android is that actually there's a lot of vendor specific QoS interfaces. So applications have to kind of pick and choose.
And that's one of the sources of information. Yes.
Yeah. And so I was going to say, let's look at things that already exist. I would maybe highlight the Qualcomm. Unfortunately, I don't think anybody from Qualcomm's here. So they have a QAPE, which is one interface that, you know, developers seem to like. Not everything in that is something that everybody agrees with, but it's one of those things where it's maybe a signal. I know Len Brown gave a talk at Plumbers a couple of years ago where he went off over the previous.
So about the Chrome, the interface used by Chrome, yes, yeah. But that has problems that the QoS values in that interface don't mean particularly anything to the kernel.
So Rafael, Lukasz, the question here is, I mean, I'm completely in sync that we need an interface to explain, you know, what the task requires. And maybe even if we consider throughput versus latency, or throughput and latency to be the two parameters, how does it translate to the kernel? Because throughput could mean increasing the CPU frequency. It could mean changing the fabric P states. It could mean, depending on where you want to locate, place the task or its cache locality.
Yeah, so, yes, it could. So,
I mean,
my
don't
personal
have
idea. My personal idea. So let me say this way. My personal idea is that the more like sensitive you declare you are, the more things would be adjusted for you to run faster, right? It's like and that depends on how. So say we use just for the total experiment, we use the parameters that Vincent was mentioning. So they are per task. So it's kind of clear what to do with them in the scheduler, but it is not at the CPU at the system level, right? For example, if we talk about interconnect, so there needs to be some aggregation function that will be applied and then used to adjust those settings based on that information. And what the aggregation function is a matter of, you know, I guess discussion at that point, but that's the way I would do it.
I mean, you in your property slide, you had an important point: easy to use and easy to understand. So I think what you are looking at, this is for experts, but what the general public, the general Joe developer wants is something he can actually understand. So there's no, I mean, we can, if we come up with a proper interface in the long run, but for experimentation, I agree, we should just start with easy to use things. You can always have I fill in this is the type A and type B I think I am. And then you have extra fields in the data structure where somebody like you can go and say, hey, this is the bigger information behind it. So I think we shouldn't go and try to design it in a way where it's actually only again accessible to power users. It should be understandable for most people and easy to approach
Good point.
information. because I mean, if you really want to get the lost 2% out of a system, you need more. And then you're equipped at the point where you can actually use the very dedicated hardware specific knobs, because then you squeeze out of your particular system the lost 2% of performance in order to utilize it better and gain. But that's not what we are looking at, because right now we have no simple and understandable way and generalized way for the application developers, and especially in the mobile space, where I can say, hey, look, this thread has these characteristics which I understand, and this thread has some other characteristics where the OS, the scheduler, the power management, whatever hangs off of this at the very end can at least deduce something. Right now, we have no information at all. And people try all these ad hoc extra interfaces, which are even worse, because I looked at some of them, they tend to be so specialized that it's not funny anymore. So, and we need to have to start at some simple point with an extensible interface, because otherwise we're going to spend the next 20 years admiring the same problem.
So I was expecting the middleware to do this translation between the application running and how to translate that in meaningful scheduler kernel value. I mean, because if you ask Android, if you ask Chrome OS, if you ask server, they all want a different interface. I mean, if they want something meaningful, they don't want to express the same thing. So we will never find, at least in the coming months, an interface that will fit for Android, for Chrome OS, for server, for IoT. What we can say, just play with your interface and then map that. We can expect to have some Android guys.
I'm fine with a mapping library. I'm perfectly fine with that. I think that's the best way for us to move forward. We have to be very careful not to expose any specific hardware properties through that interface. This has to be completely neutral in terms of these are the properties in an abstract way, which can, in a generalized way, which we then can map to the particular hardware we're running on.
Yeah.
Because if you start exposing the hardware properties again, then you have lost.
Yeah, good point. Thanks.
So to answer the Dietmar's point, like this will need to be prototyped and tested and so on. But we need to kind of like to know where to start, so we don't like go in a totally wrong direction, because then it's a loss of time, honestly. That's why I'm talking about collecting feedback from people regarding, because some of the cases that we are talking about are really simple. So there is a thread which the property of which is that when it runs, it has to run as fast as possible and without latency possible, right? That's one category of things. On the other end are those backgrounds pieces. In the middle, there is a spectrum of stuff. I don't know to what extent we could. So I kind of like the idea of extending an existing interface, because this is a natural way of developing things. But and then to the Thomas's point, that there can be a library that can be used by, so on systems where there is no middleware, and there are systems like that, right? There is no place that can translate the application settings to the kernel the information useful for the kernel, but there can be a library where you can that can be done in principle. So if you use a specific, definition, then the library will fill the values for you, and then
you said extending an existing interface. I wouldn't do that. I wouldn't recommend that.
Okay.
Make it explicitly, this is a new approach to it where we collect central information and where we aggregate things in order to coordinate all the related subsystems and entities in a meaningful way.
Right.
Because if you stick it into some existing syscall, then it becomes again something, oh, this is a scheduler property, this is a whatever. It all belongs to the scheduler suddenly, and people are reluctant. If you put it into neutral ground, people, it's just a psychological problem to define this is neutral ground. This is not owned by the scheduler. This is not owned by power management. This is an approach to actually consolidate the mess we have.
Okay. So what about the deadline part of the spectrum? Are we going to use that new information on those tasks too?
Attributes?
I mean, you will have, in the first place, we will have to deal with the information which comes from the scheduling side too. I mean, if you have a deadline task, the scheduler can feed you the information into that interface from the kernel side and say, hey, these are my properties.
All right. So, yeah.
Fun. Also the other way around, if the task, so we can, but I would start with very simple constraints just to figure out whether this actually works.
Another question, Morten?
The get deadline interface uses absolute parameters or metrics to describe what you want from the task. And we just discussed earlier that we want something which is relative.
Yeah. Well, so yeah, I would also not want to confuse people how to use the same interface different ways.
And using time. I mean, how are we going to do that on hybrid systems? How do you express latency or even throughput for a hybrid system?
Maybe we don't really want to use that and extend that, but have something else that can be mapped to that in certain cases, but is essentially agnostic about how that thing is going to be implemented. Might be just a scheduler settings map, or might be scheduler plus power management plus something else.
Yeah, so in other words, maybe the new interface can be used to produce the information needed by scheduled deadline. At least in some cases.
But what Thomas' point was, if we should better start from the clean ground.
Yeah, that was his point.
Yes, because you don't come into the situation where you start, oh, but I need to preserve this. No, you won't. And you really want to because we have done that way too long.
Yeah.
And that's what has brought us into the situation we have right now.
That was kind of my my thought that we would need to start from scratch. So one more thing, like maybe to clarify some ideas. So do we use scadat for this, or do we use a different system call, or
create a new system call?
New system call, yeah.
Make a new system call, because it's not only about scheduling. It's explicit multi-resource control.
Not for technical reasons, but for kind of clarity, right?
Or political reasons.
Yeah.
Yes, and it makes it clear that this is not only about the scheduler.
Yeah.
I mean, these power management, thermal, whatever scheduling have to interact in order to produce a functional system, and to guarantee certain aspects what an application wants, but it's not really well defined if you say everything of that goes through the scheduler in the first place.
Yeah.
Right.
To have some, because then you can build also feedback mechanisms in this infrastructure, which is separate from the scheduler core.
Okay. So a couple of things I already know. So yeah, we use a new system call. It is clear that this is not scheduling specific. We need both information coming from the tasks to the kernel, but also the other way around. We are not sure about the representation of information at the moment.
John, comment?
It's going to ask to make sure that there can be other tasks that assign for threads. So it's not necessarily something that is just the task doing to itself.
Right.
Yeah,
So
I will remember that.
Yeah.
Don't worry.
Yeah, and it needs to be dynamic. Actually, for creating a new interface that you can have a target, let's not use PID. Maybe we can use something like PID-FD or something like that, because we have issues where the PID can be reused if it's a target. So then you set the settings on the wrong PID. So let's give that some thought when we're.
And also maybe at some point being applied on a group of tasks.
Okay.
That's one. We are looking for this unicorn for 5 years.
Any other comments? Probably not. So we can probably start doing the research and experiments.
Yeah.
Okay, so thank you very much.